All right, we started the recording. Today we have this paper. I don't know if I can zoom in here. So it's 2207-03670. You have it on the archive. And one thing that we will be discussing is dynamical decoupling. It will be the dynamical decoupling for superconducting qubits. And it will be a performance survey, which will kind of tell you the state of the art last revised version on archive 2023. So it's kind of very recent. It's like less than 2 months at the time of the recording, right? So that will tell us a bit about technology, state of the art, what one can do. Okay, so that's just reading the title. So learning a bit more about what we were discussing with Schur's lemma and all this dephasing and some ideas how to remove certain operators. Superconducting qubits we were discussing, and now we will extend a little bit. Okay, so this is this paper here. This 2207-03670. It will be also the link I will add also later. Okay. So let's do a similar mode like we were doing with the engineer's guide. And let's see if I can tell you what to expect based on the abstract. Okay, so dynamical decoupling is perhaps the simplest and least resource-intensive error suppression strategy for improving quantum computer performance. Okay, so what kind of errors do we get? Some coupling to some outside system, and basically we are losing the coherence of our qubit. We were discussing this Bloch-Redfield model for decoherence. So this is some ideas that are there in the background. We will write more about the setting later. Okay, so that's just the first setting, the physical problem of trying to reduce noise, which is kind of crazy if you think about it, because how do you reduce noise? But it's possible for certain noise models. So we report a large-scale survey, and when people say large-scale survey, it means that the paper was probably very painful to write, because you have to check many things, and usually the more things you are checking, the more papers you're putting into a single paper. So a good large-scale survey is sometimes worth the work of a few papers, actually. Performance of 60 different DD sequences, DD dynamical decoupling, from 7 families of how to construct this dynamical decoupling. That's something that we will see a little bit, including basic as well advanced sequences with high-order cancellation properties inbuilt in robustness. This kind of high-order error cancellation is in some way vaguely related to Taylor expansions, and maybe undergraduate students know about Runge-Kutta methods. So you have the Euler step, for example, and you have higher order integration methods, and similar things you have also in matrix analysis, which shows up in a slightly different way, but it's kind of related in a similar way, that basically you go higher order, which means you do more operations, but you align those operations in such a way that you're canceling lower order errors, so your error becomes higher order. Something we will see. The survey is performed using 3 different superconducting qubit IBMQ devices, with the goal of assessing relative performance, with the goal of checking how well it works. Yeah, we find that the high order universally robust. So this is basically singling out the results of the analysis. If you're ever doing comparative analysis, you will see how painful it is to actually have a statement like this, that something performs better than something else, because often it depends on criteria. So we won't read the full paper, but you can read the full paper and try to check under which conditions and what's going on there, because maybe under other conditions, maybe some other sequence performs a bit better, and so on. I think in this case, it was actually a fairly simple case where this surprisingly actually caught my attention, and then it really shows in the paper. We find that the basic sequences, so those are some old sequences that are actually related to NMR, nuclear magnetic resonance. if you read Nielsen Chuang, which was written a quarter century ago, back then NMR qubits still played a role, and these days we are actually bouncing back because people learned quite a lot how to use them. And those sequences were actually developed back longer than 20 years ago for NMR qubits, and now the same kind of ideas can be used for superconducting qubits as well, which is kind of a neat thing to see that the theories are kind of wide-ranging. And that's also why we want to develop Kibo. So this kind of package that I'm also discussing sometimes here, right? So Kibo is this package which actually can run different pulses. And then one thing that we are going to be working on in Singapore is to add this dynamical decoupling into Kibo. So that's more or less why I'm also going, why I'm discussing this paper today. So those basic things can match nearly those higher order pulse sequences if you have certain intervals, and it's good if the intervals are large enough. Good. Then, unfortunately, I don't have the time to go through the introduction, but if, I don't know, somebody wants to read it in more detail, you can read it line by line, and what kind of information should you expect? There will be references, so the references will tell you the representative implementations and so on. Here you have a very nice list, for example, of operations you can do on qubits, and you have the leading ideas for qubits, which are actually selected because there are more possible qubits that you can use than I think is listed. But they are selected in the sense that this dynamical decoupling DD can be used to improve the fidelity. We didn't talk much about fidelity, but fidelity is a measure of how well a quantum protocol implemented some target state. Okay, and then there are more complications, and it's listing those citations, those references here. We don't have much time to talk about this. There are different chips that they used in this large-scale survey, and that's kind of in the background. So this is the kind of information. I think we will be fine just keeping ahead. Here's a little bit of context and a little bit of background, how to understand the gates that we need. We will go back if we will need the full names at some point. So dynamical decoupling background is something we can do more or less line by line, because that will explain to us the setting. Okay, and that's a nice tutorial, and that's maybe one comment to you. If you are new to reading papers, sometimes a piece of a publication can be actually useful. So don't read line by line often. Try to see which parts you can understand, and those parts will be useful to you. And then the parts that you really need, you try to grind. Okay, if I skip ahead and you see this kind of stuff, you look at this, you don't understand this, maybe it's not collapsing the whole reading of the paper. Okay. But it can also happen that you have a very neat tutorial that will teach you a bit about physics. Then if you don't know it at that time, you're learning physics from a publication and not a textbook. But this is more or less something that could be in an extended version in some textbook. Okay. So consider a time-independent Hamiltonian here. And we need to understand what are those letters here, because each H will be a Hamiltonian, okay? So HS and HB contain terms that act respectively on the system and the buff, okay? So I will have my qubit Q, which is actually the system S. And then there is also a buff. So what can be the buff? It can be a kind of nature around the qubit which is taking a photon, which a photonic wave packet, which is localized here because it got emitted with some energy of the electromagnetic field in this box of space here. And the environment will be propagating the photon, which means the buff, which is our environment, has some Hamiltonian that allows the photon to propagate. Yeah, if this would be an identity, this photon would be standing still, and you know exactly that photons go at speed of light. So there has to be some Hamiltonian HB, which if the photon escapes the qubit, will propagate the photon to the edge of the universe, for example, right? So that's the meaning of the buff. There can be also another thing is that the buff can have, for example, some atoms, and a photon here can be absorbed. So you could have also something that is maybe absorbing some photons on the way. So the photon maybe escapes to the edge of the universe, or there's some atoms, some galaxies that capture the photon or whatever. Of course, in standard treatment, you won't be doing, you won't be modeling the entire observable universe as the buff. You will have a much simpler Hamiltonian for the buff, and I will check in a moment if we have some examples. But that's just kind of the mindset, what we are interested in here. Okay. And so you will have also the qubit HS, which is Quantum Engineer's Guide to Superconducting Qubits, and we know by now what kind of Hamiltonians we can get. We mentioned SQ circuit, so whatever you get from those kind of papers and studies would be HS. Okay, so this is this line. HB is more or less the ambient vacuum that is maybe transporting away the excitations, and HSB is an interesting case where you explain what are the matrix elements that take out energy from my system and put that energy into the vacuum around the system. Okay, so HSB will be always the coupling between the system and the buff. It's a very generic setting. You will often find this kind of stuff. Okay. So we write HS, which is HS0 and HS1, where HS1 represents an undesired always on term due to crosstalk, so that H error is exactly this, and you want to cancel this stuff. So this represents we wish to remove using DD. Okay, so if you were confused, what is this dynamical decoupling? This dynamical decoupling is a method that allows you to remove portions of a Hamiltonian. So normally I would have the evolution e to minus ith, where h is given by equation 1. But now I want to do something in my system so that I will turn this into ith as 0, which is my desired state, plus hb, but there's no HSB, so this kind of factorizes, and at some point you can forget HB, which means dynamical decoupling is a method that allows you to engineer that desirable portion of the Hamiltonian. Okay, HS contains all the terms we wish to keep. Again, we are lucky, good writing. So, no, sorry, I was talking ahead while it's written here already. All right. Maybe I put it back in case somebody wants to see. The corresponding free unitary evolution for duration t or tau is given by ft, which is a unitary parameterized by the duration t, which is just the exponential here. If I would use tau and not t, we would have the same formula, so we're good here. Okay. And now DD is generated by additional time-dependent control Hamiltonian HCT using purely, which is acting purely on the system. So H of t will have our desired term, our undesired error terms, which are acting both within the system, so we want to kick it out, and acting out of the system. HB we can leave because as soon as we remove HSB, there's no coupling to the environment, so we are happy. And then additionally, there's the control. How do we get the control? We were talking about adding some LC oscillator, and capacitively coupling this to our qubit. So we can have a superconducting box, some capacitor or some element. So this would be some transmon. And here we could be pulsing with voltages. We were talking about those voltages as a function of time that then translate into some couplings that enter into the Hamiltonian. Okay, so basically this HCT is either you're doing this for some atom, which means you have some cavity and you're pumping some laser light into this, but this laser light is pulsed in intensity in time. So sometimes you have some stuff going in and sometimes not. So this could be the laser intensity of some light going into cavity, operating and the qubit shaking it up in this controlled way, or it could be the superconducting qubit control that we discussed. Okay. Let me check if there are some questions. Oh, there were some questions. Okay, so there's a question about a boson field. The buff can be a bosonic Hamiltonian or not. In my case, I was indicating that it's a photon just to give you an example. On a quantum dot, so let's say I have a quantum dot on some substrate. You want to have a defect which is capturing a single electronic state, and that's called a quantum dot. So here you could have some processes where electrons or charges are taking away the coherence of a quantum dot. So this would be a fermionic buff. If you have an atom sitting in an empty universe and you're emitting outwards photons, then this would be a bosonic buff because it would be bosonic modes. And now the question is how many modes you have. There's only one special case where you only have one mode, which is the standing wave, the principal mode of the cavity, for example. Otherwise, if you have free space, then you have continuous distribution here. So you have eigenfunctions which are ikx, and here you have cosine. The cosine k would be actually 1 probably, and then some position here in the cavity. Okay, so usually your buff will have many modes, and because it has many modes, it's hard to control them. And even if you're in a cavity, the cavity actually is outcoupling to such a buff. So in principle here, a cavity is a way of having a nicer environment, but it doesn't solve everything. Okay, so usually this buff component is so nasty that you cannot have any control of this. One example here, an atom emits a photon, so good luck trying to catch the photon and put it back. Actually, people manage to do this, and the way you do it is with the cavity, but the cavity is not perfect, so then you have some more issues. Okay. There's one more question. So we choose microwave frequency in general. There are certain things that you can choose, but that's not the point of the paper. The paper is saying this is quite general, and you might have certain particular frequencies. Those frequencies show up here as omega 0. That could be microwave. And that's the range of maybe electromagnetic transitions that you would use for typical qubits, whatever qubits were listed in the introduction, but usually are more or less microwave regime. But it can be whatever. We are, this is, I mentioned that it's a little bit like a textbook because this could be any physical system. Okay. So if you have I don't know, a huge system, which is not microwaves, but some other, frequencies, then it's still fine. You could try to apply this system as well. This is very important that you understand that this is our outside control, and this is what we can do. This we can't modify because you cannot control the galaxy around our atom, right? So the photons escape and we have no control over that. Okay. And now we are going to a new paragraph talking about what is an ideal pulse sequence. And that's a pulse sequence that doesn't have errors and is instantaneous Hamiltonians, okay? Which means that you are, imagine you have the atom, and this atom has some kind of Bloch sphere oscillation, some Rabi flopping or something. And now if you come in with a huge light, which is acting maybe like sigma z rotation, but the intensity is so large that basically this z operation applies maybe a pi rotation in a time where this qubit doesn't even move with its natural frequency on the Bloch sphere, okay? So this is this idealization where you assume that you're in a regime where the control can be such a strong force that the qubit in that time doesn't move on its own, okay? Which means that that this control here is a Hamiltonian that acts in those kind of spiky ways. And in the moment when it's acting, you forget the system Hamiltonian. So basically you put this to 0 because this is driving so much evolution that in that time this doesn't do much to your physical state in the lab, okay? So let me give you an example. E to I A plus alpha B applied to a state psi, okay? If alpha is very huge, then this becomes more or less I alpha B, okay? And we know how to quantify this because we were doing the perturbation bounds, we were doing matrix norms and so on, okay? And now this case is a bit more complicated because you have to trotterize, because here we would have some ramp that is ramping it up. So basically I could have e to I delta t A plus alpha B, and then this alpha maybe is changing as a function of time, and I do this e to I delta t A plus alpha prime, some other value of this alpha, and then I change the alpha on the way. That alpha is implementing this pulse, because if I'm switching on the pulse, it means that my B term is acting in that moment in time, okay? But you see locally here, if this alpha still is much, much bigger than this A, then you can forget this A, and you get this idealized pulse sequence where it's acting with those Hamiltonians here, okay? So this is just an idealization to say that you can kick a system and forget that it has its own inertia, okay? It's an instantaneous kick model. And to substantiate that, I can highlight this instantaneous Hamiltonians.
So you're doing that just for the ease of calculation, or are there any more deeper reasons?
Yeah, so I'm not sure if in this paper they explain or study the difference whether you use this idealization or not. Yeah, but you could in principle study what happens if you have a finite ramp and you don't have those infinite forces in the system. Yeah, but
is it clear that those infinite forces are sufficient in a sense? Like,
sufficient for what?
is it known that only with those like infinite forces you can do everything that continuous variations can do?
Oh yeah, because then you would just take more of it and then you're fine, right? So
because you can like put many places.
Yeah.
Okay.
Then you just do again this Nyquist theorem. So if your desired pulse is like this, you can use Nyquist to just have finite samples that kick in, and at some point you have a similar signal. So that's roughly this. And Nyquist is actually, if you do matrix analysis, this is Trotter-Suzuki, our discretizations as well. At some point we are implementing this continuous evolution up to negligible error. Yeah. So we have this pulse sequences. This is just to say, this is the bridge between saying that nature is continuous and smooth, but sometimes there are those abstractions of kicking something, yeah? So you imagine some billiard balls, and then you would say this is just a single cake or something like that. And those abstractions are very useful because it's easier to think what kind of sequences will do the job. In the lab, it will be actually not this ideal, perfect, instantaneous, and all those adjectives, but these abstractions will be good enough. And you will see, you know, if you scroll down and read the full paper, you will see that this dynamical decoupling works quite well. Okay. So now what we are doing is, maybe you're getting lost a bit in what I'm saying, because you need to add a bit of reading. If this is new to you, then it's just that that you're learning a bit more about the framework of quantum control. In quantum control, you have this kind of setting where on the outside sometimes the pulses will dominate this evolution. So those pulses will kick in and they will have this kind of spiky form. And so the total evolution will be adding up here by adding the pulses. Okay. So this is a bit of a sidetrack, but there's giving you a background, as the section title says, and so on. Yeah. So we didn't discuss dynamical decoupling yet. Okay. So if you, from this discussion, if you didn't learn how to switch off this undesired error term, is because we didn't explain that yet. Okay. But this is a setting that we need because this gives rise to instantaneous unitaries or pulses. So pulses are physically applied as voltages or laser fields, but they translate to different controlled unitaries, where this here is forgetting about the system inertia in some way, because the pulse was so strong it dominated that evolution. So then you introduce this notation where you apply this instantaneous unitary to your state. Okay. And now the total evolution, if we have a sequence of schedulings that I have certain pulses P1, P2 acting at different times. Okay, so I have pulse 1, pulse 2, pulse 3, but this duration here is long. Then the qubit can rotate in qubit or qubits, they can do some evolution here. So you have the idle evolution here for the duration of T2, T3, or tau3, or whatever, those durations here. You need to include that because maybe you're not always pulsing, and maybe you actually want the system to be able to evolve sometimes on its own. Just let it be sometimes, right? Will added these control pulses introduce any errors? Yeah, they add errors, but if you do them well, they are actually helping you. Okay. So we will see that so this comes at a cost. It's a very good question. Actually, you're anticipating the limitation of the method, because ideally you would like to do it as fast as possible. So those pulses are like this, and then they will stabilize the system ideally, but they have their own errors as well, and that will limit the application of this. There will be a limit of how fast you can pulse. Okay. Okay. Good. So if that's fine, we can continue, because we can quickly go to first order protection at some point. But let's see if we get some comments, because I'm not sure, maybe there's some background that is useful to say. The unitary U of t, which is U0 of t bt, can be decomposed into the desired error-free evolution U of t, which is just the system Hamiltonian and nothing on above, and the unitary error B of t. Okay. Why can we do this? Well, unitary group U of D means that that for any group element G, there exists an inverse also in the group. Okay. So if I have a unitary, which is an element G, and I have another unitary, which is an element G prime, then I can relate them multiplicatively by saying I take G, and then G prime minus 1, it will give me some Q. And now if I invert this, I see, okay, G is actually G prime times Q. Q is sort of like the residue evolution. But you can always decompose the undesirable thing or the imperfect. Which one is perfect? Desired evolution, okay. So this is what we are able to do in the lab. This is what we want to have in the lab. And this is some unitary, okay? If we can show that this B minus identity unitary is epsilon, then as a small exercise, let's check. Then U of t minus U0 of t. Using this decomposition, I can write U0 B of t minus U of t. This U of t I skip, U0, okay? Then I'm pulling out U0, I have B minus identity. Question in the chat, what will we use now to relate to this error? It's a property. You need to know the name because in that way you're using a mathematical lemma to transition from this to this. But once you know that property, you will see that you can reduce to B minus identity, and by construction, you know that this is maybe epsilon, which means the implementation in the lab and the idealized evolution are implemented up to this epsilon. Okay. So anybody want to say, you can unmute yourself or put in the chat.
Do we need to correct this P part? Because it's only acting on the pulse, right?
The B is unitary error BT. Ideally, BT is acting only on the buff. Then it's not a big problem, but sometimes there will be an error. And
Okay.
as small as possible, this B part, it could also be acting on the system.
Okay. I didn't really. Okay.
Could be. But here I just did a bit of matrix analysis, yeah? And the answer is that we use unitary invariance of the norm, which means that if I have unitaries V, sum of matrix A and another unitary V, then the norm is just take the norm of what's in the middle. So in this case, our U is V here, and here we have an identity multiplied here. So my A is B minus 1. Okay, that's how we use this lemma of unitary invariance of the norm. Okay. So that's this decomposition that you can in principle always do. And then you would like to reduce this B of t. And that's something that you can do in QTIP. You can do some numerics and so on. Okay. I think okay, then we continue. So now we will see DD. And 9050 is what I said with NMR. I gave you already a little bit of the background, so we will skip the background. It's worth reading it. I think I enjoyed actually reading it. So there's some intuition maybe how to do the DD, but let's have a look at this. Let's have a look at the setting. We will make the discussion more precise. We write HB and HSB in a generic form for a single qubit. So HB is this, HSB is like that. And here we have the coupling to the buff. Okay. So what is this notation? Sigma alpha, when alpha is equals to 0, so sigma of 0 is identity. In this case, we are collecting HB to be acting on the buff only. Okay. When alpha is non-zero, then we are coupling some buff operator to the qubit, which is implementing HSB. So the 0 term in this sum is doing HB, and the remaining 3 terms are doing HSB. Okay. Since distinct Pauli operators anti-commute, then for k non-zero, if you conjugate H by unitaries, exercise, you can prove that Pauli X, Y, and Z operations are unitary. The two-dimensional unitary group, okay? So we are actually conjugating this by a unitary. And what do we see? We see that if we conjugate it by Pauli X, then for non-X Paulis, we are flipping the sign here. And the Pauli X is, of course, invariant. It stayed the way it was. Okay, which is the dephasing that we were discussing last time. So if I have a matrix and I applied the following channel to it, it's a 2 by 2 matrix in this case, maybe. And I apply the channel in the sense that I do Z, A, Z. Then if I have A, which is, for example, X, then I have Z, X, Z, which is minus X. And here I have identity acting it, so A, which would mean I have X minus X, which is 0. And that's the cancellation, cancelling terms. So we were talking about this using a bit of group theory motivation that it is possible to make summations with unitary conjugations around the operator in such a way that those conjugations is averaging over something will give us some 0. Okay. And today what you're seeing is that if I do this with Pauli X, then for Pauli Y coupling to B alpha, I get a minus sign, while X coupling to BX stays the same. And then the idea is that you have X and just the evolutions, and this is called the pure X cancellation, and that will have certain properties that we want to see. And then what dynamical decoupling does in general is that you do it for X, you do it for Y, and you do it for Z, and at some point you remove everything that you had, right? So we are acting on the qubit in such a way that we want to remove how X couples to above operator, how Z couples to N, and so on, okay? So then we get this induced effective Hamiltonian in the sense that we are going to be applying a minus X rotation, X rotation, and then the evolutions. Okay. So this notation is maybe a bit weird. Ft is defined around here, which is just the pure evolution with the Hamiltonian. Okay, so we have stages of pure evolution. The system is running, and here you are disturbing the system with this X operation. And this is we use X interchangeably. I guess it would be maybe a bit better to use just one of them, but yeah, you can check it in the appendix. And really, for such a paper, 38 pages with 60 different settings, it's like, you know, at some point you need to bring out the paper. So sometimes you will see those kind of notations like this, and that's maybe something that's, you know, that you should understand, that this is just impossible to have like a streamlined two-page paper about something so complicated. Okay, so anyway, we get this Hamiltonian, and there's another method, CPMG, which is similar to this, but you have two evolutions for half a step size, so it's more symmetrical. It says here, which is symmetrized placement of the process. Okay, good. So this PX sequence does something, and intuitively it removes the XYZ. So if you would not be coupling by Z to your buff, then you can use Z. So if you don't couple by X, then you can use this X to remove everything else, and you already cleaned it up, and you're fine. Okay. There's some discussion of what we were saying already, so I will skip that because we want to see XY4. And what's going on here? You are pulsing with Y, you are pulsing with X, and you're pulsing with X again. Okay. And basically, by adding a second rotation around Y, the XY4 sequence defined like this cancels the remaining sigma X terms, right? Because our X rotation removes the Y and Z terms, but it keeps the coupling to the buff of X operators. So now we do an interlacing with Y, which is canceling those as well. And then if you follow the paper fully, then the added evolution of how this composes is like you put them up together. This is Zasenhaus formula, is exactly what we are doing with Trotter-Suzuki decomposition. We actually proved the bound here with this T squared, getting the constants correctly with the commutator of the norm and the norm of the commutator of the operator. So we saw this in previous tutorials, yeah? So this is in the background, and we don't spend time on this today, okay? Good. So that cancels the remaining terms, and you see that the effective Hamiltonian after this XY4 is acting like an identity in the buff. So the buff just is doing its own evolution. It's like a galaxy far away, doing its own politics, and I don't know, being bored or studying the same system, but we don't talk to the buff anymore. Okay, that's the magic of those cancellations. So let me show this in a simpler case. If I have, let's say I have an X evolution, if I consider Z and Z here, and again X here, then I can use the unitarity as we were saying to do this, EX. And then if I can add them together, I will get minus X plus X, which gives me an identity. That's the kind of calculation that is running in the background. Okay. And now to do it correctly, this should be a small evolution time delta t, which in the notation of the paper is tau. So here you get tau, here you get tau, and now this will be cancelling plus O of t squared, because non-commutativity here adds another term here and here plus OT squared here as well. Okay, so that's the only thing that is missing here. Another thing is that you cannot just switch off the evolution in the moment where you're applying this pulse. So it will be actually a slightly different evolution. It will be in this case delta tx or delta t some other duration of the z pulse, and then here z acting in this moment. And there's I everywhere, I here. And then you have e2i delta t x. So you see, sometimes this x is still acting, but it should be basically with some epsilon, it should be much smaller. That's why we can neglect it, and that's why we just put z, and then we have the idle evolution, z and idle evolution. And then if you want, you can replace in the notation this with h, with the full Hamiltonian. Okay. I flash it out again a bit, but it's maybe not very nicely written.
Sorry, where did that order of t squared coming from again?
What is coming what?
So that you put this error proportional to like tau squared. Where is it coming from again?
This error?
Yeah.
Yeah, because if I connect those two, in this case they are commuting, but in general, if there will be a Hamiltonian here,
I see. Okay.
and that's this kind of Zassenhaus discussion. Okay.
And ZHZ is not minus Z in general because of the Z term there? Or?
Yeah, ZHZ is not minus H in general. Good exercise. Try to find an example. So let's say there's a wrong statement and you need to write, let's say for all H Hermitian, you claim ZHZ is minus H, and you can find a counterexample to it.
Yeah. I guess just Z.
Just Z.
Yeah.
So basically the commuting stuff with Z doesn't get flipped, but the off diagonal gets flipped. That's why the dephasing channel uses Z. Okay. And exactly what we discussed here, that there's a counterexample to this. If you now switch the angle and go from X to Y, you will now cancel the remaining stuff. And this is exactly what they say here. It's canceling the remaining terms. And achieves universal first order decoupling. Decoupling, you see now what's the name, because there was a coupling to a buff, and now there's no decoupling. To first order in the pulse speed. Okay, but we had a question in the chat whether those pulses introduce errors, and they do. So you cannot pulse infinitely fast, and there will always be a little bit of this error. But what this paper very nicely shows is that there will be some plots. Let's go to the plots. Methods. It's a long paper, but you see time average fidelity here and so on, and there will be certain pulses which are improving things. without doing anything, you will have 0.6 average fidelity. If you use all those UDD methods, you're improving the fidelity by what? 30%, 0.6, 0.9. We don't reach unit fidelity. It's not a perfect system, but it works. Okay. So that will be the end product of those pulses. Yeah. A priori, when we were thinking here of this general design of the method, you cannot know how well it will work. You need to actually test it in practice, not only with numerics. And that's the point of this paper. It's really hard work to evaluate all this stuff. Okay. Higher order protection is basically doing it recursively. Okay. So there are nested concatenated dynamical decouplings that are just nesting starting from this XY4 sequence. XY4 sequence, we know what it is. You use X conjugations to remove X terms, and then you use Y conjugations to remove Y terms. Okay. And now you could refine this, always taking shorter pulses and so on. So you do some X and Y pulses, and you do this previous CDD there. And the point is that it will improve your error. But the next section will be nicely explaining that there will be some cutoff how well you can do it, and there will be some competition of errors. This is more careful analysis, implies that if epsilon tau is on, it is sufficient to provide error suppression. CDDN has some optimal concatenation level, because at some point you are making too many pulses, and there's some scaling here with some prefactor here. So there is the corresponding concatenation level, and this is this kind of stuff. Okay. So for the undergraduate students, it's like the equivalent of exercises in physics. You do this kind of exercises like, this is going well, this is not going well, where will it be optimal? Then you put it in your paper as equation 20, and then that's the kind of results that you get as a product of your research. Yeah. As an exercise, you can have a look at this notation and check whether you are understanding everything here, because we were covering operator norms. Yeah, and this is a nice paper because it's giving it to you. Usually you will have to use it, look it up on Wikipedia. Okay, we're almost done. This is an interesting subject here. At some point it gets very involved, and it's basically very sophisticated how to do things better. Then you can account for final pulse width. It will teach you about time-dependent Hamiltonians and some applications of that. We don't have time for this. Where this PK evolution is actually what? This is a time-dependent Hamiltonian. That's the standard notation that people use for the unitary that arises from the Schrödinger equation, where the Hamiltonian is time-dependent, and you're applying the Schrödinger evolution from this tau k to tau k plus delta and so on, right? And then in the limit of some delta of the pulse being extremely short and this omega growing, you get this idealization here that we discussed. Okay, so you can read this, but it will be more detailed, more advanced, and you can have a look. Then usually you will need also some testing models, and so you can optimize certain things. It gets complicated, okay? But then you can keep reading, and sometimes you can skip like I do, because maybe we want to see some examples. Yeah, so here you will have some figure that explains to you some physics, representative samples of our results, DD sequences. And then you look at the fidelities. For example, 5 qubits together, you improve the fidelity up to 90% thanks to those DD sequences. But errors are stochastic in the sense that they are randomized, so you will have certain error bars. So you see this UR20 has the smallest variance here, but its average is kind of maybe nasty. So maybe you want to risk it a bit more and use a different method, and then you never know. And that's why those large-scale surveys are so difficult to say, because you don't really know what people will be interested in, and you need to kind of account for different things, and it's making it very difficult to write it up. This is really something that you can try reading still. Just don't get stuck with the details. Okay, this is a new development in physics. That's actually a very welcome thing that is making our whole field better. You can actually pull the code and check whether you understand the packages. You can try to run it yourself. Yeah. And you see that's just like several different languages, and you know, unless you have worked yourself on a larger comparative analysis, you might not expect how tough it is to put everything together and finish such a project. Okay, appendix might be useful for somebody who wants to implement those methods, so you might want to have a look. If you want to study more, you just look in the appendix. I'm just skipping ahead to see if I can find something to say, but I think I just skip until the end and say we read the full paper. Okay, we didn't read the full paper. I was just giving the introduction. You can read line by line, but this two-speed way of reading papers I very much recommend it, because if you would be reading it line by line, it can happen that you get stuck somewhere here. While we managed to get maybe more or less some ideas, we understood equation 20, that there will be some trade-offs. So we understood many things, and in principle, using those equations, you can understand what kind of sequences you're running. And then you know what is behind maybe your favorite one. You say like, okay, maybe I want this one. And you can look back at the definition. Maybe you don't need to know all of them, okay? Because maybe you won't learn that much. The authors did the work here. Good. Then we are finishing this, unless, let me check, no questions. I think I will stop here and not take any questions. Yeah.